Okay, so in this lesson, we're going to be discussing the antiderivatives of functions involving exponential and logarithmic functions to the base e. Now, in another lesson, we're going to be discussing such antiderivatives where the exponential and logarithmic functions are given to any base a. However, this lesson is only specific to the exponential function and to the logarithmic function to the base e, which are y equals to ln x, and the exponential function would be y equals to e to the x to the base of e. Now, as usual, in order to build the rules of integration for these functions, we're going to use their derivative rules in order to build the rules of integration. So we do know that the derivative of e to the x is e to the x. Y equals to e to the x, the exponential function to the base e, is unchanged by differentiation. So consequently, it's unchanged by integration. So over here, the integral of e to the x would be e to the x. However, the derivative of ln x is 1 over x. So the integral of 1 over x should be ln x. However, you'd notice that we have x in an absolute value here. It's for a reason that ln x has a domain of 0 to positive infinity. Ln x is only defined for positive x's. However, 1 over x is defined for all real numbers except 0. So the domain of 1 over x does contain negative values of x, which for ln x cannot take these negative values. So it's for that reason that if you're starting with 1 over x over this domain, in that case, when you integrate, you'd integrate into ln of the absolute value of x in order to avoid ending up with negative values inside of ln. Now, if it's given that x is positive, in that case, you could remove the absolute value. But if x is not given to be positive and you're working over the domain of 1 over x, which is all real numbers except of 0, in that case, you'd have to integrate it into ln of the absolute value of x. However, before we move into putting these into examples, I just like to note that if we just refer to the power rule of integration, the one that we've seen in a previous lesson when we actually introduced antiderivatives. So the power rule consists of x to the n, the integral of x to the n dx, which is 1 over n plus 1 times x to the n plus 1 plus k. However, an equivalent rule consisted of integrating 1 over x to the n, and we did justify in that lesson this rule using the power rule, which is negative 1 over n minus 1 x to the n minus 1 plus k. Now, it would be good to revisit that first lesson on antiderivatives in order to remember the integration of basic functions. However, the integral of x to the n, we know that the power rule is actually valid when n is different than negative 1. Because when n is negative 1, that would be a 1 over 0. So this rule can actually be applied where n is any real number except negative 1. Because when n is negative 1, I'd have the integral of 1 over x, where we've just seen that the integral of 1 over x is not in fact a rational function or a polynomial, it's logarithmic. So it's for that reason that this rule does not work for n equals to negative 1, and similarly the second rule for n equals to 1. You'd notice it would work for all values of n except a 1, because at 1 you would end up with negative 1 over 0. So 1 over x is in fact a rational function whose antiderivative is not rational. Its antiderivative is in fact logarithmic. Now let's just put these rules into examples here. So The first one is actually very easy. Now 4 is a constant. It just goes outside of the integral. Now the integral of e to the x now is e to the x because e to the x is unchanged by differentiation. So here the integral of I would in fact be 4 e to the x. Now similarly here, this constant 3 does in fact go outside of the integral, if you want to just put it that way. So the integral of 3 times 1 over x would in fact be 3 times the integral of 1 over x. And we've just seen that the integral of 1 over x is ln of the absolute value of k. Now over here we're not given that x is positive, so x could be any non-zero real number. So in that case, the antiderivative ln x would actually x would actually take the absolute value here. Now these are two simple, direct, straightforward in order to start with the examples. Now we're going to start taking it a little bit further. Now over here we have the integral of e to the 5 minus 3x. Now, this is an exponential function to the base e, and we do know that the integral of e to the x is e to the x plus k. However, I'd notice here that instead of x, I do have 5 minus 3x, which is linear. So being linear, being in the form e to the u, where u is linear, I can use the compound formula here. So in our antiderivative, whatever we have x, I replace by 5 minus 3x, but I do not forget to divide by a, where a is the slope of the linear expression here. So it's a negative 1/3. Now, putting that into I, so over here, I would actually be negative 1/3 times e to the 5 minus 3x plus k, and that is using the compound formula. Now by looking at the second one, now of course the two can be isolated outside the integral, could multiply the whole integral. However, we'd be left with 1 over 1 minus 3x. Again, that being linear, that would in fact remind me or consider it in the form 1 over x, where the integral of 1 over x is ln of the absolute value of x plus k. However, instead of x, I have 1 minus 3x. So in my antiderivative, I replace x by 1 minus 3x, and I do not forget to divide by a, which is the slope of the linear expression I'm dealing with here. So in that case, I would actually be, now don't forget we already have a 2 here, so it's 2 over negative 3, which is negative 2/3 times ln of the absolute value of 1 minus 3x plus k. Okay, now moving it a little bit further. So here you'd notice that I have an exponential function where the exponent is not linear, so I cannot be using the compound formula here. However, when the compound formula does not work, we do first start by checking for the substitution method. So whenever we have an exponential function, so I could start by considering that in the form e to the u. So if I consider this in the form e to the u, then I would be considering u to be x squared plus 1. Now, in order for the substitution method to actually work, I need the derivative of u to be present in the integral. So over here, by differentiating u, the derivative of x squared is 2x. The derivative of 1 is 0, so that would leave me with du equals to 2x times dx. So looking at the integral, I've noticed that in the integral I have x times dx. I do not have 2x times dx, and that's okay when the difference is just a constant. So here, dividing both sides by 2, I could end up with half du equals to x times dx. Now, I'd like to remind again the importance of the differential here, because whenever you have u prime is in fact du over dx according to the Newton's notation of the derivative. So du, the differential of the new variable, the one you're introducing, is u prime times dx. So this is why du is not just 2x, it's not just u prime, it's u prime times dx. So this is why it is very important to have the dx here in order to be writing mathematically correct, so that dx comes from the fact that we cross multiplied here in Newton's notation. So now going back to our integral, x times dx can in fact be replaced by half du, and x squared plus 1 by, which leaves me with I equals 2. Now don't forget that from x dx we have a half here, so it's half times the integral of e to the u du. Now e to the u du, now our variable of integration here is u, so the integral of e to the u is e to the u. And now we bring back our expression in terms of x, which is half e to the x squared plus 1 plus k. So that is our first integral. Now moving to the second one, now we notice here that we need to integrate x squared plus 1 over x cubed plus 3x. However, just by looking at this expression, it might seem like we have not really seen a function in that form, or we cannot really fit it into a general form. However, since the denominator, the degree of the polynomial at the denominator is 1 minus the degree of the numerator, in that case, I could possibly check if the numerator is the derivative of the denominator. In that case, I could use the substitution method. So over here, by considering the denominator to be u, x cubed plus 3x, by considering du, now differentiating, we'd have 3x squared plus 3, all of that times dx. Now I'd notice that in my integral, the numerator is not 3x squared plus 3, it is in fact x squared plus 1. However, I'd notice that if I divide both sides by 3, I'd end up with 1/3 of du equals to x squared plus 1 times dx. So there you go, x squared plus 1 times dx is 1/3 of du, where u is the expression at the denominator. So in that case, I could use the substitution method. If du did not turn out to include the numerator of the expression, in that case the substitution method would not really work. We'd really have to really look for another method to use there. But over here, what made me think of using this method is the fact that the numerator has a degree that is 1 less than the one at the denominator. So in that case, the numerator could potentially be the derivative, because the derivative of a cubic polynomial is a quadratic polynomial. So I do check for it there in order to check if the substitution method works, and it does in fact work. So over here, that would leave me with 1/3 the integral of 1 over u times du. Surprisingly, that is the derivative of ln of u, so that's ln of the absolute value of u plus k, which leaves me with I equals to 1/3 ln of. Now u is x cubed plus 3x, so that's the absolute value of x cubed plus 3x plus k, and that is antiderivative or an antiderivative corresponding to this second integral we have here. So again, in our following lesson, we're going to be integrating such functions to the base of a. We're going to generalize to a general base.